So this is what we're doing when we measure an elevation angle. That celestial horizon, that's the equatorial plane. And those two lines there, the artificial horizon and the celestial horizon, they're parallel lines. That is only available in Euclidean geometry. That's what we're doing when we measure elevation angles, when we do anything to do with celestial navigation. This is a Euclidean proposition 30. Straight lines parallel to the same straight line are also parallel to one another. This is only available in Euclidean geometry. These are Euclidean axioms. Number one, a straight line can be drawn between any 2 points. Number two, a finite line can be extended indefinitely in both directions. Number three, a circle can be drawn with any center and any radius. Now that's Euclidean geometry, a circle, a nice flat 2D shape. Number four, all right angles are equal to one another, to each other. And number five, given a line and a point not on the line, only the line can be drawn through the point parallel to the line. That is the Euclidean parallel postulate. So parallel lines, they are lines that do not intersect each other. That was what we saw in the first slide with the artificial horizon parallel to the celestial horizon or the equatorial plane. The parallel postulate is valid only for the Euclidean geometry. There are many other geometries, which is non-Euclidean geometry, for which parallel postulates is invalid. So under the heading curved space there, Euclidean geometry is flat. Imagine you have a piece of paper and a ball. A piece of paper has no curvature. The surface of the ball is curved. There is curvature. Curved space cannot be described by the Euclidean geometry. Therefore, it is called non-Euclidean. In curved space, there is a characteristic length scale r. An example is the surface of the Earth. Spherical geometry. It's basically the surface of a sphere. All lines will eventually intersect. No parallel lines exist. You cannot do anything to do with celestial navigation, parallel lines, artificial horizon, parallel to the celestial horizon or the equatorial plane. You cannot do that on a sphere. In spherical geometry, the sum of the interior angles of a triangle is greater than two right angles. Pi equals 180 degrees. In flat geometry, which is Euclidean geometry, the sum of the angles of the triangle must always be 180 degrees. The circumference of a circle, this is another point here too, the circumference of a circle is less than pi times the diameter. That's in spherical geometry. In flat geometry, the circumference of a circle must always be pi times the diameter. That's what we're doing when we work out the circle of equal altitude. If you look on that picture, that's for spherical geometry, you've got a circle there. That circle on the sphere, that circumference has to be less than 2 pi r. That's not a Euclidean circle. You cannot put a circle of equal altitude, a 2D shape, 2D circle, on a spherical surface. It does not work. This is the circle of equal altitude that we are actually working out from Euclidean geometry. That is a 2D circle. The circumference of that circle is 2 pi r. You cannot put that on a spherical surface. This is what they think they're doing. They think they're putting a circle of equal altitude, a 2D shape, onto a spherical surface. It does not work. We are only using Euclidean geometry in celestial navigation. If you think you're doing anything with the sphere, you need to use spherical geometry. They do not compute. We are living on a flat Earth. Euclidean geometry is flat Earth geometry.
So Mitchell showed this. In fact, we have a couple of slides that, unbeknownst to each other, we shared this morning. You can see here, this is the subpoint method as described, figure 14.1. And you see the 90-degree box, even though it's not a box, but it is 90 degrees. So you can put a box or you can put the angle there. And it says here that you have a co-altitude, and it uses the observer's zenith, and it also has the zenith of the star. In this case, GP over the Earth is called the subpoint. And then the observer's position would be the observer's GP. And you can see those are two vertical zeniths. And then the co-altitude on top, as well as the baseline on the bottom, are key to this, because if your height observed is 60 degrees, as shown here, then you minus that from 90. And when you minus that from 90, 60 minus 90 is 30. 30 times 60 nautical miles is 1,800 nautical miles zenith distance. That top straight line, the co-altitude, will match that baseline exactly. So you are on the Earth's surface, 1,800 miles away from that star's position that's posted in the nautical almanac or the air almanac. So you could do another circle of equal altitude and a third and get a fix, and you know where you are in relationship to where they are. This is pretty simple, well documented, and it needs a 90, always a 90. Next slide. So what happens when you're on the surface of a sphere, and Mitchell shared this slide as well, and you need to do this when the baseline is curved? Well, you use an artificial horizon, a bubble section, for example, because this is from the air navigation book that I bought, and you create a plane called the artificial horizon. And it's going to match the celestial horizon in their celestial sphere model, where the Earth's equator keeps extending outwards until it hits the celestial horizon, and then it keeps extending until it hits the celestial sphere at an infinite distance. You have a plane. Well, as long as you have a plane that's on top of a plane, and the stars are so far away, the angle is going to be the same as long as that light from the stars coming in parallel. So the key to their whole model is using a plane and star or sunlight being parallel. But really what they're doing is letting the cat out of the bag by showing that all the navigation stars that are used are based from the center. And what do you see there at the center of this circle, but it's supposed to be a sphere? You see a baseline all the way through Earth, all the way to the celestial sphere. So if all measurements are coming from a plane at the center and it goes all the way to the celestial sphere through space and everything else in their model, then really all they have is flat Earth measurements. And what they do with an artificial horizon is they use a bubble to give them that horizontal at their eye line, which is either called the astronomical horizon or the sensible horizon, because that's where their eyes are. This can never be done when using a marine sextant using the Earth's horizon, which is the surface of the Earth, because they have to do dip correction to get their eye onto the sea level, height of eye correction. And you know they're in trouble when they keep referring to angles. You don't need a right angle. Okay, well, when we go to the previous slide, if you would, what you see there in the subpoint method is two right angles. It's a box with 4 90s. You could put a 90 at every corner there. This is how it's done. And when they keep saying they don't need right angles, they're fooling themselves. You need a right angle. You just can't get one off a curved surface. So they use a bubble section or artificial horizon, and you say 2 lines is all I need. I don't need to minus from 90. Well, yes, you do, because you need a right angle triangle. And it's always the follow-up. Once you get your elevation angle, no matter which method you use, whether you use a tray with mercury, or you use a bubble sextant, or you use the marine sextant and shoot the Earth's horizon from the surface. Guess what you have to do once you do corrections to get true altitude, which is right angle? Guess what you have to do? You have to minus from 90. But it's a right angle triangle that you minus from. So how could they say it's not? Next slide. So this one shows co-altitude and zenith distance from a side-on view. And you can see here in this one, it's a 40-degree elevation angle taken not from the surface, but the center of the Earth. And you see that parallel line going right through the Earth with the dotted part, and then it becomes solid all the way to the celestial horizon, all the way to where the stars are in the celestial sphere. That's a flat plane, buddy. And you've got a 40-degree angle from that flat plane. And so you minus that from 90 is 50. 50 times 60 is 3,000 nautical miles. That whole globe picture is a joke because they're never getting it from the surface that's curved. They always get it from the flat plane, equatorial plane. Next slide. All about angles. Right angle measures exactly 90 degrees. An acute angle measures less than 90 degrees. An obtuse angle measures more than 90 degrees. The right angle is the one being used for Earth. The acute angle is your measurement prior to minusing it from 90. That could be anything from 5 degrees up to 89. It don't matter. The acute is the angle of elevation. It must be minus from 90, the right angle above, to get your co-altitude. There is no obtuse angle in celestial navigation. Next slide shows a picture that shows the Earth, the equator, and the celestial equator, the equinoctial, you might say, all the way to the celestial sphere, as you can see here. It's just not showing the stars here in this one diagram. All right, so you could see where right ascension is at 0 equator line. They have to have that 0 baseline. It's 0 all the way to the stars. It's 0 on their circle as well. Next slide. Celestial equator divides the sky into northern and southern hemispheres. If Earth's equator is projected out into space, celestial equator can be obtained. Well, they're just telling you right here what they're doing. It's a plane all the way from the center to the celestial sphere. And all the nautical almanac measurements are done from that equatorial plane, which means it's all flat surface, because it has to be an angle, has to be minus from 90. I'm done. Any questions?
No, that's perfect.
I'd like
Other than to say that it's redundant, or not redundant, useless. When you take this circle, so I'm just going to go back to your, I think it's your first slide, and you've got this circle, and it's showing you 90 degrees being measured below the star, and there's your position, and here's the circle that you're drawing out after getting the GP from the almanac and the time. That's what you end up with, right? That's the circle. If I now go to your last slide, that's the same circle. This massive disc that runs outside of this tiny little ball that's in the middle, that's completely useless in terms of the measurement, because if the star was up at this arrow point and you were measuring its GP, it would be parallel to your GP, which would be running to the center of this sphere that's totally not used and useless, and then out along this disc to 90-degree point below the star. So that would be your box in this diagram. So you've got your GP, and you're measuring it according to them on the equatorial plane. That means you're in the center of their rock sphere that isn't used in this measurement. And then 90 degrees out to the base where, on that flat plane, the star's ground position is, its geographical position, its GP. Well, that's also a 90 degree at this position, from your feet to where the star meets at 90 degrees. So this bit in the middle, the globe, totally useless in that process, because what I've just drawn out with the zenith of the observer in the middle of a rock that's not being used and out to the GP of the star, that square, that box that I'm now drawing on screen, correlates to this box. But not only that, the circle that's being drawn out in this particular example can be bigger, because you can draw out more circles to other stars, all on flat planes. But all of them must have 90 degrees for this box, for everything to be parallel. Now, as soon as you curve the ground, these stop being parallel, and the functionality of celestial navigation breaks down. You need it to function on a flat plane, and it does.
Everything that you just described there, Nathan, is Euclidean geometry. Can you go back to 10's first slide? If we go through the Euclidean axioms, number one, a straight line can be drawn between any 2 points. So a straight line from the observer, the ground beneath the observer's feet, to the GP of the star, that's a straight line. Number two, a finite line can be extended infinitely in both directions. That means the plane, that straight line, that can extend infinitely. That creates the equatorial plane. Number three, a circle can be drawn with any center and any radius. This is a Euclidean axiom. A circle can be drawn with any center and any radius. That's what we're drawing with a circle of equal altitude, a 2D circle. It is flat. Number four, all right angles are equal to each other. We can see that with the zeniths. Those two right angles, 90 degrees, they're equal to each other. And number five, the parallel postulate, those two zeniths are parallel to each other. These are all Euclidean geometry. As soon as you say sphere, that's spherical geometry. We haven't described anything to do with spherical geometry, anything to do with a sphere. This is all flat Earth geometry.
Not only that, in the depiction, which is why I like this, because now you can highlight where the magic trick comes, they've drawn a bent line. I mean, it completely violates what's being described to have this line bent, and they've even marked it as 90. So obviously they're aware of it to a certain level, because they can't get 90 off a curved line. But they've drawn it that way because obviously this has come from a book where on the last page of the last description, it'll also disclaim that obviously you're still on a ball though, despite everything being detailed mathematically and only capable of being done on a flat plane. But they'll still bend this line. Well, no, this isn't a 90 if you want to now say, oh, look at this diagram's describing this as a great circle. That would be their great circle. But their great circle gives them 90 degrees. My bad. Doesn't give them 90 degrees. That's their problem. The only critique on what Mitch said earlier, this is how we do it. This is how celestial navigation is done. Just in case anybody says, oh, Mitchell said it's... No, this is just the method of celestial navigation and the facts that surround it.
It's about the distance and about the angle to the GP. So you can draw it on your chart, draw a line there, and then you do it for all three, and you get your intersection. So it is actually triangulation. You can draw a triangle, solve the triangle, and know the angle that the light or that the object must appear to be. And so we can do triangulation, but we have to presume that the Earth is flat. But if you're doing triangulation, you do a triangle on the surface of flat Earth, presuming flat Earth, you get then
you need three lines and it is a right angle triangle. You need the horizontal baseline adjacent, you need the hypotenuse angle line, and you need the opposite, which is the zenith from the GP. To keep forgetting with that, that is the third line of the right angle triangle. So every time they come up with this, we only need two lines, you remind them of the zenith from the GP, because the adjacent and the hypotenuse, right? The adjacent, which is the horizontal along the surface of Earth, the hypotenuse, which is the angle line, they must meet the opposite, which is the zenith from the GP. So the people who are saying these things are crazy, and as Tent says, they cite themselves. They don't cite anything really official.
In simplified terms, when we take a sextant altitude of the sun, we're creating a right angle triangle between it. The Earth's surface at the GP and ourselves, grade school geometry tells us that the two angles in the right angle triangle must equal 90. How they get around this is impossible. If they want to take one of those things out, at the end, you must minus from 90. What's a 90? Why can't you just do it off the surface of a curved Earth? Because it's impossible to get an angle with a curved baseline. Stage of the sextant.